Okay, now we know that there are different degrees of infinity. Now we know there is some quantity beyond the infinity. So let's try to come up with at least one set which is larger than our natural number set. So we have not yet analyzed the real number set. So what about the cardinality of real number set? So far, I had assumed that even numbers are smaller than natural numbers, integers and rational numbers are greater than natural numbers, but they happen to be of the same quantity. So now I will start with assuming that real numbers are also equal in numbers with natural numbers. So we have the cardinality of real number is same as cardinality of natural number. I will assume this. Now since this assumption, there is bijection from natural number to real numbers, which means I can make them stand, I can make the real number stand in a queue. I can list them down one after another one. Why I can list them down? Because I have, for every real number there is some associated natural number. So in that sequence I can list them down. The real number mapped with 1 I will write it first. The real number mapped with 2 I will write it second. The real number mapped with 3 I will write it third. So I can make them stand in a queue. I can list them. Okay. So let's try to list down all the real numbers over here. So again I am for simplicity I will ignore the integer part of the real number and I am only considering the fractional part of the real number. So this is my first real number. Let's say this is digit 1 of real number 1. This is digit 2 of real number 1. This is digit 3 of real number 1, 4, 5 and so on. So this along with these digits gives me first real number. 2 1, 2 2, 2 3, 2 4, 2 5, 3 1, 3 2, 3 3, 3 4, 3 5, 4 1, 4 2, 4 3, 4 4, 4 5 and so on. Since natural numbers are infinite, this listing is infinite. So I have many real numbers, but all the real numbers may appear here or somewhere. All the real numbers are in this list. There is no other real number which will not be part of this list. And I can say this because I have assumed that number of real numbers are same as number of natural number. So my assumption is all the real numbers are present here. Okay, let's try to build one other real number. So how I am building this other real number? So this is D11. So there are in all 10 digits I have. So this is one digit out of those 10 digits. So I will choose any digit other than D11 for my D-1. First digit of real number to be constructed. Now the second digit, I will make sure that the second digit will not be same as D22. That will be my D-2. For the third digit, I will choose any other digit other than D33. So that will be my D-3. So my four digits, let's say D44 is 5. So I will choose any digit out of 0 to 9, but I will not choose 5. I will from 0 to 4 and 6 to 9, I will choose any digit for D4 dash and so on. Now, this is a real number. So this newly formed real number should present somewhere in this list because our assumption is all the real numbers are in this list. So let's try to match this real number with all the entries in our list. So let's take this. Is it same as this? Is this real number same as this real number? Surely not, because these two numbers differ in first place. I have made sure that this D1 dash is not same as D11. So for sure this is not same as this number. Okay, let's compare this digit with this number with this number. So these two numbers differ at second place. I have made sure that while construction, this D3 is not same as D33. So this number differs at the third location, this number differs at the fourth location, this number differs at the fifth location. So at these locations, so you compare this number with any number in this listing and this number will differ at the diagonal position. So this number is not present here, here or anywhere in this listing. But our assumption was all the real numbers we are able to list them down, but now we have one real number which is not in the list. Okay, let's add this number over here. Let's say at last I will add d1 dash, d2 dash, d3 dash and so on. Okay, now I feel that I have completed the listing. Is it? So let's try to build one more real number. Again using same strategy. So d2 dash. So for this d double dash 1 will differ from d11, d double dash 2 will differ from d22, d double dash 3 will differ from d33 and so on. So at some n, if this is the nth number, the new entry is at nth position, d double dash n will differ from d in n. Again, if we compare this newly formed number with all the entries in our listing, they will not match. These two number will not match at this location, next will not match at this location and this location. So again we have one more extra element. Our assumption was all the real numbers are present here, but now even if we do this many number of times, we can come up with one real number which is not part of. So our assumption is wrong. That our assumption that we can list down all the real numbers is wrong. That is why we get a numbers out of the sequence, out of the listing. This approach is again called as Cantor's diagonalization approach for real numbers. And this Cantor's diagonalization approach for real numbers tells us that we are not able to form a cube out of real numbers. So we have ignored the integer part. So let's say let's keep it constant. So we are not able to arrange the real numbers between 0 and 1. If for this sequence we are not able to arrange, forget about the entire real numbers. If we make this 1, we are not able to arrange the real numbers between 1 and 2. Forget about the real numbers beyond these two numbers. And why this is so? So our assumption is false. So our previous assumption was that real numbers are equal in number with natural numbers. That is false. So real numbers are much larger than natural numbers. And why this is so? If this is my real number line, this is 1, this is 2, this is 3, this is minus 1, this is minus 2, this is minus 3. So if it is integer number line, we have seen that this integer number line can be converted. Somehow I can shuffle the integers and then I can find the mapping. So, but for real number line, this is infinite in this direction, this is infinite in this direction, and this is also infinite in this direction. There are infinitely many real numbers between any two real numbers. So there is an infinity over here also, and because of this infinity, we are not able to map all the real numbers with natural numbers. So what is our method of counting? We pick up the number, we pick up the element, and we map to the next natural number. We pick up the next element, map to the next element. Now pick up 0, map with the first natural number. Now which element you will pick? Will you pick 1? No, you should pick 0.5 before 1. So will you pick 0.5? No, you cannot pick 0.5 because there is 0.25. So you should label or map 0.25 before 0.5. So will you pick next 0.25? No, there is 0.125. Will you pick this? No, there is some other element. Will you pick that? No. So because of this infinity, you are not able to pick up the next element to count. and because of that there is no a bijection between number of real numbers and number of natural numbers, or real number elements and natural number elements. And that's why the cardinality of real number is larger than cardinality of natural number. And Cantor gave symbol to this quantity as aleph 1. More on this aleph 1 in next 2-3 minutes. Is it really aleph 1 or something else? We will see. But the point over here is real numbers are larger in number than natural numbers. And to prove this, we have used Cantor's diagonalization approach for real numbers. Okay, now let's talk about this aleph 1. So we have natural number set whose cardinality is aleph 0. Then we have real number set, let's say whose cardinality is aleph 1. Now for this real number set, I can form power set of real number set. And according to Cantor general theorem, power set of real number set will have cardinality of power set of real number set is larger than cardinality of R. Let's say that is aleph 2. Again I can form power set of real numbers. And the quantity over here is larger than quantity over here. So this quantity is greater than aleph 2. Let's call it aleph 3. So I can go on building the power set of power set. So tower of power set, I can go on building this, and then I can get the higher and higher degree of infinity. So from aleph 0 to aleph 1 to aleph 3 to aleph 4 to, so what will be the end of this line? So if you observe this, aleph 0 can be mapped to 1, aleph 1 can be mapped to 2, this to 3, this to 4. So there is 1-to-1 mapping between all these alephs and natural numbers. So all these set of all these alephs are equal in number with natural number. So what is the cardinality of natural number? Cardinality of natural number is aleph 0. So I can go up to aleph 0. And at this point, Cantor raised his case and said that this is the biggest infinity I can imagine, or one can imagine. Okay, so now we already know one more set which has greater infinity, which has greater quantity than n, which is power set of n. Now where does this power set of n lie in this sequence? Is it equal to aleph 1, or is it equal to aleph 2, or aleph 3, or some aleph n, or is it somewhere between here? Maybe aleph 0.5, sorry, 0.5, or somewhere here aleph 1.5. So I will get a larger infinity than aleph 0, maybe aleph 1. When I will get aleph 1, when this will get mapped to real numbers, when I will have some infinity which I can associate with 0.5, when I will have some infinity which I can get associated with 0.25 or 125 or 0.0001. So if this sequence is real numbers, is corresponding to real number sequence, then I can have aleph 1. So the next point is, can we have this kind of infinities, the infinities of fractional infinities? And this is still an open research topic. This is called as continuum hypothesis. We don't know yet whether there exists aleph 0.5 kind of infinity or not. Is it a real number like line, or is it a natural number like line? We don't know it. This is continuum hypothesis. So since we don't know whether this is 0.1, since we don't know, should we name it as aleph 1 or aleph 0.1 or aleph 0.1? We discarded this kind of notion now, this kind of notations, because we don't know whether it is 0.5 or 0.1 or 1. Is it natural associated to natural numbers or real numbers? We don't know. So we discarded these notions. We also discarded this aleph 0 notion or label given by Cantor. Now we use C symbol to represent number of natural numbers. C stands for Cantor. And because of continuum hypothesis, we don't know whether this kind of infinity exists or whether this kind of infinity exists. So what we know right now is infinity is not a single coherent object. It has multiple degrees. Some infinities are smaller than some other infinities, but for sure there is something beyond the infinity. There are these many infinities which are beyond the infinity. That's it for this topic.